Howdy class. So today we're going to be talking about something called intermolecular forces. So you might have heard of these before, but if not, you're going to get a crash course on them right now. So this is going a little bit out of what we've been talking about, but it's related, so that's why it's here. So liquids and solids are called condensed phases because of their density. So they are condensed into a smaller area or a smaller volume than the gas phase. So you see here the liquid and the solid, sorry, that was a weird line, are both they're more condensed. They're squished into a smaller volume than the gas over here. So that's because they have higher densities. So liquid and solid water or ice, have similar densities, but water vapor is less than 1% of the density, less than 0.1% of the density of liquid and solid water. So water vapor, the gas form, is so much less dense. And this is a result of intermolecular forces between particularly the molecules in liquid water and ice. So, but in more general terms, liquids and solids have higher densities because of the intermolecular forces between the atoms or the molecules that make up those liquids and solids. So the physical state of a substance, solid, liquid, gas, and whatever else there is, plasma, Bose, Einstein condensate, anyway, so the physical state of the substance depends on pressure, temperature, and intermolecular forces. So we're going to talk mostly about intermolecular forces. Pressure and temperature are important, but they are related to the intermolecular forces, so we're going to focus on that. Intermolecular forces are the forces between individual particles in solids, liquids, and very, very weak intermolecular forces in gases. So intermolecular forces I call IMFs. So intermolecular forces are not chemical bonds. So these are not bonds. Chemical bonds are between atoms within a molecule. IMFs are forces between separate atoms or molecules in the pure substance as a whole. So if we're talking about a pure substance such as helium gas, or if you cool it down a lot, so down to 4 degrees Kelvin, super, super, super cold, then you'll probably have some intermolecular forces between helium atoms in that pure substance. But usually we're talking about forces between different molecules in a pure substance. It's just very rare cases where we talk about atoms making up a substance. So in other words, chemical bonds hold the atoms together in a molecule. Chemical bonds make the molecule. IMFs hold atoms or molecules together throughout the liquid or solid substance. So chemical bonds are teeny tiny scale. IMFs are very teeny tiny scale as well, but throughout the whole system. All right, so we're going to go back to our good friend Coulomb. The strength of IMFs depends on the charges on the nearby molecules that lead to the electrostatic forces of attraction. These attractions follow Coulomb's law, so this is the force version, so it's R squared. The energy version, where it's just R, same difference. It has the same trend where charges are on top, distance in the denominator. Anywho, this is the force version. So one type of intermolecular force involves ions with discrete charges and polar molecules with partial charges. So ions like sodium ion or magnesium ion interacting with polar molecules like water that has partial charges on the different atoms in the water molecule. These are called ion-dipole intermolecular forces. So when polar molecules like water. So this is our little water structure. You should recognize water and why it is bent now after the rest of chapter 7 that we've done so far. Anywho, when polar molecules like water approach an ion, an electrostatic attraction forms with a strength that depends on 1, the magnitude of the charge on the ion, and 2, the ion's size. So, Coulomb's law. The charges matter, the size matters, because the size is going to affect how close the molecule can get to the nucleus, the center of the charge on that ion. So if you notice, this is water molecules interacting with cations, and that's because we have the negative end interacting with these positive ions. So oxygen is the more electronegative atom in water. So that's where we have the partial negative charge. That's where the electrons like to reside primarily. So that's the partially negative end interacting with the positive ion. And that makes sense because electrostatic forces are opposite charges. Anywho, we can see here that sodium has a weaker interaction than magnesium, which has a strong interaction with water. So they're both pretty strong, to be fair, but the magnesium interaction with water, the magnesium intermolecular force, ion dipole intermolecular force with water, is stronger because magnesium has a higher charge. It's a +2 instead of a +1, and it's smaller. Sodium and magnesium ions, these two ions are going to bring in more terms here that you should be familiar with. Isoelectronic. These are isoelectronic ions. So the one with more protons is the one that is smaller, and that's magnesium. So magnesium has a bigger charge and it's smaller. So higher number on top and smaller number on the bottom. Both of those things make the force stronger. All right, so that's one type of force. So we already know about ionic bonds. We talked about them back in chapter 5. That's when we transfer electrons from one atom to another. Now we're talking about these intermolecular forces that are not full transfers. These are not full bonds. These are just interactions. So now we talked about ions and dipoles. So now we're just going to talk about dipoles. So we're going down in our energy here. So ion forces like the ionic bonds in chapter 5, those are the strongest forces holding things together based on the discrete charges, the full +1 or +2 charges on those ions. Then we have ion dipole, where one of them is still an ion, but the other one is a polar molecule. Now we're going to talk about dipole-dipole forces. So as we know, charges on particles within a substance are not usually discrete charges. They're usually partial charges. We usually have polar molecules, not fully ionic molecules. There's a lot more polar molecules out there in the world than ionic molecules. So dipole-dipole intermolecular forces are attractive forces between two polar molecules now, instead of a polar molecule and an ion. All right, so when polar molecules like HCl approach each other, so two HCl molecules coming together, an electrostatic attraction forms between the partial positive and the partial negative ends. So if we call, I don't remember what your book calls each color, but I would guess that red is the negative end. I think that's usually how it works on electron density maps. And blue is the positive end. So in that case, this is the H, this is the Cl. So we've got an HCl molecule, hydrochloric acid molecule, and it's interacting with other hydrochloric acid molecules. So if it's in the solid form, then they're going to be really well ordered. They're going to be stacked like this so that positives are by positives, negatives are, or sorry, positives are by negatives, negatives are by positives. We have, you know, alternating red-blue patterns in this solid. Liquids are a little less ordered. Liquids aren't as dense, so they aren't squished together as much, typically, and they aren't very ordered, so that's why a solid has a defined shape and volume, whereas a liquid has a defined volume but not a defined shape. It conforms to the shape of its container. And that's because liquid's a little more disorganized. So it can mold itself to different shapes. So here we still have the same thing happening, red, blue, partial positive, partial negative. So you can see that overlap. It's not as pretty as in the solid, but it's still there. And so generally speaking, dipole-dipole intermolecular forces are weaker than ionic and covalent bonds. So they're weaker than chemical bonds in ionic solids or covalent compounds, the things we've talked about mostly up until now. And they are generally weaker than ion dipole intermolecular forces. So we're going to talk about these in levels of decreasing energy for the most part. Or sorry, yeah, decreasing strength for the most part. Unlike what your book does, where it puts ion dipole at the end for some reason, I didn't like that. So I put ion dipole first, and then dipole, and then we'll keep going. So just another note here, dipole intermolecular forces between the hydrochloric acid molecules, the HCl molecules, allow HCl gas to condense into a liquid at low temperatures. So the stronger the forces are between the molecules, the more likely it is for them to be a liquid at a low temperature instead of a gas. So gases have weak forces between them. Liquids have stronger forces between them. So if we have strong dipole-dipole forces, like we do in HCl, it's got a pretty nice dipole, then our gas condenses into a liquid and we have liquid HCl at low temperatures. That is its natural state at like room temperature. And those molecules are held together by a network of dipole-dipole forces. Looks kind of like this. These are noted as dashed lines because these are not bonds. These are just intermolecular interactions. They're not full bonds. Okay, so these are our discrete HCl molecules. We condense, so this is a gas, and this is a liquid. And this happens naturally. So as you lower the temperature, gases become liquids. Kind of the same thing that we have with water. So the boiling point of water is 100 degrees Celsius. When we drop below 100 degrees, we condense into water. We go back to a natural state. Same thing happening here. And then this little table down here that I got from your book just shows some different structural formulas with their corresponding dipole moments and boiling points. So the thing to note here is that as the dipole moment increases, so does the boiling point. So what that means is the stronger the forces are, the more you gotta heat it up to break them apart. So the higher the boiling point, because we're going from this liquid state to this gas state when we reach the boiling point. So we need a higher boiling point to break away things with stronger forces between them, which comes from having higher charge differentials in our molecule. So the higher dipole moment means we have a more polar bond, which means we have stronger dipole-dipole intermolecular forces, which means we have to heat up our liquid higher to get to the gas form where we break apart those intermolecular forces. So they're not bonds, but they still have a strength. They still have a force, an attractive force holding them together that you have to undo to get to boiling. All right, so moving on, hydrogen bonding is a very strong type of dipole-dipole intermolecular force. So this is a subcategory of dipole-dipole intermolecular forces. And it's a little unfortunate that it's called bonding because hydrogen bonds are still not chemical bonds. These are still not bonds between atoms. These are just intermolecular forces, electrostatic attraction between molecules. They're not bonds. So it's a little unfortunate that we call them hydrogen bonding, but it is what it is. Anyway, hydrogen bonding only occurs between molecules with these three types of bonds, never anything else. No hydrogen-hydrogen bonds, no carbon-hydrogen bonds, no chlorine-hydrogen bonds, just hydrogen-nitrogen, hydrogen-oxygen, or hydrogen-fluorine bonds. Those are the only ones we consider hydrogen bonding molecules. Anything that contains an HN bond, an HO bond, or an HF bond can have hydrogen bonding. Anything that doesn't can't have hydrogen bonding. Not significant for us to call it hydrogen bonding, at least. So what's special about hydrogen bonding? Hydrogen bonding is really strong for two different reasons. So one, the elements that are bonded to hydrogen are very electronegative. These are the three most electronegative atoms on the periodic table, fluorine, oxygen, and nitrogen. And hydrogen has a pretty low electronegativity. So we put something that's really electronegative with something that's really low electronegativity, then we get highly polar bonds. So really strong dipole-dipole forces. This results in strong partial charges, or sorry, large partial charges. So closer to 1, like closer to +1 on one end and -1 on the other end. Still partial charges, but closer to full charges, leading to a strong force of attraction between the molecules because of Q1, Q2 being on top of our Coulomb's law. Next, hydrogen is very small, which allows hydrogen bonding molecules to be close together, which is where our R comes in Coulomb's law. The short distance leads to strong force of attraction between the molecules. So when the numerator gets bigger, the force gets stronger. When the denominator gets smaller, the force gets stronger. So we have really strong force of attraction between these molecules. So that's why hydrogen bonds are special, and that's why we differentiate them from other types of dipole-dipole intermolecular forces. All right, and here's something that shows that visually. So hydrogen bonding occurs with HO bonds, HN bonds, and HF bonds. We have one of those. We have HO bonds in water. We have an HF bond in hydrofluoric acid, HF, and we have NH bonds in ammonia. And let's compare them to methane down here with a carbon hydrogen bond, which does not allow for any significant hydrogen bonding. The boiling point of methane is super, super low. There are no strong forces here. No strong IMFs. Because it's got a low boiling point. But oxygen, nitrogen, and fluorine bonded to hydrogen have strong IMFs, which are reflected in their high boiling points. So again, just like with the dipole-dipole interactions, when we have a high boiling point, that means that we have strong intermolecular forces. And then we go back to all these other things that don't have hydrogen, oxygen, or hydrogen, fluorine, or hydrogen, nitrogen bonds. All these other things, they have lower boiling points too, until you get up to some really big ones out here that start to overtake ammonia. But just comparing the same period, hydrogen The HO bond, HN bond, and HF bond have a significant impact on the boiling point compared to this guy down here. All right, so which of these following pure substances would hydrogen bonding be expected? Let's do a little practice here. Hint, diethyl ether has a boiling point of 34.5 degrees Celsius, whereas 1-butanol has a boiling point of 117 degrees Celsius, so a lot higher. So what's the difference between these molecules? They look like they have the same molecular formula, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens on both. 1 oxygen and 4 carbons. Yeah, they have the same formula, but they have different bonds, different orientations of their atoms. So one of them can hydrogen bond, the other can't. This one has an OH bond. This one only has oxygen-carbon bonds. It doesn't have an OH bond. So this one can hydrogen bond, this one can't. And that's reflected in the boiling point. The boiling point of 1-butanol is much higher because it can hydrogen bond, and hydrogen bonds are much stronger than other intermolecular forces, other dipole-dipole forces or whatever. Okay, cool. And then we can also consider what kinds of molecules would hydrogen bond with water. So this is a little bit of a different question. Same concept, but now you gotta have water in the mix and compare. So when we are making hydrogen bonds with water, so the hydrogen is always between the two electronegative atoms. So we need something with an oxygen, a nitrogen, or a fluorine for these hydrogens to bond to. This molecule has carbons and a chlorine. No oxygens, no nitrogens, no fluorines. We can't hydrogen bond with water with this molecule. What about the next one? Ethyl propanoate has an oxygen here and an oxygen here. So it has a couple oxygens that can bond with this here hydrogen on the water molecule. So that's a yes. This one can hydrogen bond with water. And then down here we've got hexane, which is a hydrocarbon. It's got only carbons and hydrogens. So this one's a no-go too. It doesn't have any oxygen, nitrogen, or fluorine to bond with water. Now, it's important to note that ethyl propanoates can't hydrogen bond with itself. There are no OH bonds on there for it to hydrogen bond with another ethyl propanoate molecule. It can only hydrogen bond with water because water is donating that hydrogen, that OH bond, to the hydrogen bonding system. Okay, I'm going to stop here and start another video.